All right, the next recording I want to talk about more ways of doing calculations and things that have to do with reactions in solution. In order to do so, we're going to be looking at molarity and solution volumes and solute moles and solute grams, and particularly volumes of one reactant needed to react with a given volume of another reactant solution. The last topic on this list will be a separate recording. When we're talking about chemical reactions, we look at them in very generic ways. We think about A and B reacting to make C and D. When we balance the equation, we put in coefficients for A and B and for C and for D. And what we're looking to be able to do is to figure out what volume of one solution is going to be required to work with or react with completely for a solution, some volume of solution B. It could be C or D from this generic looking equation, but let's just talk about A and B for this example and see how it works out. Well, what it boils down to is paying attention to your units. Units are your friend, and write things out, all the steps, and you will be more successful. Otherwise, we miss stuff. There's just no shortcut for being thorough. Until you're proficient with these things, unless you find you've done this 150 times, well, then maybe so. But probably most of the time you're much more successful if you are thorough and write things out. So in order to come up with the volume of one thing relating to the volume of another thing, we always have to go back to moles, because moles are how things react in a balanced equation to do products, make products. And so in order to figure out the number of moles, given a volume of something, we're going to use molarity. And then how many moles of A reacts with moles of B becomes a question of a mole ratio. We're going to use the mole ratio of the coefficients of A and B. And then once we know the moles of B, to determine its volume, again, we can come back to a molarity, because molarity relates moles and volumes, moles and liters specifically. This is a generic looking formula or setup, but we'll demonstrate how this can be used in a few examples. There is a diagram in your textbook that lays it out in a vertical fashion, but it's got the same information, and maybe it's another way of looking at it that helps you think about it. A and B could be A and B and C and D. We don't care which ones these are referring to, but A and B are just examples from this balanced equation. So always you're going to start off with a molarity as your first conversion factor and a molarity as your last one, and in between is going to be mole ratios. This feels a lot like other stoichiometry problems we've done before, except this time we're using molarity instead of molar masses. Very much the same. Write it out so the units will cancel and you'll be much more successful. Just unit conversions in action. All right, so pick an example. Let's do some sulfuric acid again. Let's see what kind of sulfuric acid volume is going to be needed to react with 50 milliliters of 0.1 molar sodium hydroxide. In order to do this, you always have to have a balanced equation. Balanced equation is step one. So make sure you have that in front of you. If not, you have to write it out. Typically, they save you time and provide it for you, but if in doubt, you better be sure it's available. Okay, so this is an acid-base kind of reaction. This is an acid. We're going to talk about reaction types soon. But there's an acid, there's a base, and when you're done, you're going to neutralize it, as it turns out, and you end up with a salt, sodium sulfate. Whoops. And characteristic also is to have water. Now, so what we have to think about is the volume of what amount of the solution of sodium hydroxide is available that provides us the moles of the sodium hydroxide that are reacting. And then if you know how many moles of sodium hydroxide are reacting, you use the mole ratio between the sodium hydroxide and sulfuric acid to determine how many moles of sulfuric acid are needed. And if you miss that step, you'll make an error. And then again, once you know the moles of sulfuric acid, its molarity can be used to come up with a volume. So the steps are kind of the same, but we got to write them out so that we make sense and understand how the units cancel to give us an answer that's credible. Okay, so let's write this one out and be as stepwise as possible and see if we can figure out where we're going without using the previous slide as our template to see what we're going to do, without putting all of the parts in there exactly, without telling you what's the conversion factors. Maybe we'll think about it. So we're going to start with the volume of sodium hydroxide. So 50 milliliters. We're going to watch our units again and make sure we're doing okay. And in order to get 50 milliliters of sodium hydroxide, write all the parts in, because sometimes we're looking at the wrong things when we don't write it down right. And we're going to use, to figure out its molarity, how many, moles, we need molarity. I gave it away to you. And so that is 0.1 moles, I'm not going to put in all the sig figs here, moles of sodium hydroxide per liter. This is a little bit like our previous examples with dilutions, where sometimes you can just stick with milliliters and there's no particular consequence. Whoa, pardon me. My tool just decided to be renegade. Rogue tool. See if I can fix that. All right, bear with me and we'll see how the units make sense. So recognizing that at the end we're also going to be looking for a volume, and probably in milliliters will be convenient. Let's leave this one in milliliters for starters, and we'll see how everything comes together in the long run. So I said we would use molarity first, right? Molarity to get the first conversion. And now, having used that, assuming that the units are going to work out, then trust me, they're going to. We'll next use a mole ratio between the sodium hydroxide and the sulfuric acid. But if you didn't write out your steps, you don't know what to put on the bottom. So what needs to cancel is the moles of sodium hydroxide. And on top, it's going to be relating to the other species of interest, sulfuric acid. And now we go to the balanced equation. So it's 2 moles of sodium hydroxide for just 1 of sulfuric acid. Without that step, you're going to be off by a factor of 2. It's a very common mistake. But notice if you've done that, now the moles of sodium hydroxide have dropped out of the calculation. Okay, so if we stopped right there, we'd have moles of sulfuric acid, but that's not what we want. We want to know the volume of this solution. So in order to do that, again, the middle step was called a mole ratio. Don't forget that. And so the next step, guess what we're going to use? It should be the same thing we used before, is molarity. And so molarity of the other one, now it's the sulfuric acid. So it's the sulfuric acid's molarity that goes in here, but pay attention to what has to go where to cancel. Moles of sulfuric acid needs to cancel, so put that on the bottom, moles H2SO4 per liter. That's what molarity means. Remember that molarity is always moles per liter, and we're going to use it that way to make sure it cancels. And so how many? It's 0.25 moles per liter of sulfuric acid. Having done that, if we're paying attention to your units, moles of sulfuric acid is canceled, but guess what else? Now liters is going to cancel. And so we didn't have to convert anything from milliliters to liters and then back to milliliters at the end. So all that should remain now, if we've set up all the steps correctly, is milliliters of our H2SO4, sulfuric acid. All right, get out your calculator, pause the recording for a minute and take a look, see if you can do it yourself, and see if you got the right thing, see if you get the same thing that I do. If you've put it all together correctly, you should get the same thing I did. I got an answer of 10 milliliters of sulfuric acid. Now, what's we do with sig figs here? This is always a worthy conversation. Pay attention to how many sig figs you had to begin with. In this value, you had 3 sig figs. Here we have 3 sig figs. Here we have 3. Well, guess what? They're consistent this time. And so this answer should be reported to 3 sig figs, which would mean that you have to put in another decimal or a value after the decimal, so it's 10.0 milliliters. All right, that was one way of setting this up, following the steps using molarity twice and a mole ratio in between. Let's think about another way to approach this problem that sometimes you're going to look at these things and go, wait a minute, I have no idea what to do. So here is another way to think of the problem and see if this makes any sense to us. It's really kind of the same thing, but it's a different way of talking about it as you go. All right, so same reaction. And we have to figure out how many moles of sodium hydroxide are available to react with the sulfuric acid. So you're going to take your volume of the sodium hydroxide times its molarity that was provided on the previous slide, and that tells you by the time you've converted this to get the milliliters converted here. The milliliters to liters conversion is needed here because the answer, or the volume of the sodium hydroxide was provided in milliliters. And if you're paying attention, all these things should come together, and we can cancel out the liters, and you get a number of moles of your sodium hydroxide. 0.005 moles of sodium hydroxide. Do we care what that number is? Not in a hurry. But we need to figure out then from that how much sulfuric acid is going to react with it. So what volume of sulfuric acid is needed to go with that many moles of sodium hydroxide? Start with the moles of sodium hydroxide and then determine from the balanced equation how they have to react with one another. Every 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. So here's another mole ratio, and paying attention to this should show you that the moles of sodium hydroxide will cancel at this step. The moles of sulfuric acid is getting us closer, but what volume is what we're still looking for. So we need to use the molarity again. And so this is molarity, and this is a mole ratio. Pay attention to this fact that we're using the same things a lot. And this one was also molarity. I didn't label it. Molarity. And putting that all together, the moles of sulfuric acid will cancel. Now it's just a question of doing the math. Put it in your calculator successfully, noticing that if you have not paid attention to your parts, something won't come out right in your units. If you don't write it all down, you won't see it. And then I'm trying to advance my device here. It's being stubborn. And then again, we're going to do the milliliters to liters conversion at the end here because we're probably thinking in terms of milliliters of solutions, not liters of solution. And when we do that, we get 10 milliliters, the same thing we had before. But it's a different way of thinking about it. You can think in terms of the moles of sodium hydroxide that are present and what amount of sulfuric acid reacts with it. We're essentially doing the same steps, but you're kind of stopping in the middle to describe the amount of the sodium hydroxide that's being reacted with the sulfuric acid in question. All right, let's do one more problem, and this one's a little bit different. This one will take some more steps and more thinking. It's a little more complex than some, but I hope that it feels helpful to you as being an example of another way of doing reaction stoichiometry calculations. But this time we're going to look for how many grams of something could be used. Okay, so let's say you've got a flask of this acid. It's hydrobromic acid. It's a cousin to hydrochloric acid. And it's got 350 milliliters, and you spilled it. Oh dear, it's a strong acid, and it's not good stuff. You need to clean it up. So how many grams of potassium carbonate would be needed to neutralize the spill? To do that, we need to recognize what equation is involved. And this equation is laid out for us so we can just insert some coefficients. It's actually far simpler than you might first imagine, but this is good practice all the same. Take a look, see what you can see that's the most obvious thing to begin with. Well, I would see that you clearly need to have twice as many potassium on the right. Put a 2 here. And then what else do you need? It looks like hydrogen needs to be balanced, right? And so in order to do that, you also affect the amount of bromine, but that works because putting 2 in front of HBr on the left means you get 2 bromine on the right and 2 hydrogen on the right. So hydrogen checks, bromine checks, potassium has checked, so they've got 2 on each side. But what about the carbonate? Carbon with 3 oxygens. Well, there's 1 carbon. Well, so far so good. But we have 3 oxygens here, and you have 2 plus 1. Well, how about that? It was far easier than you first imagined. So no more coefficients are required. Now, I'm just going to write this one in. This was not an autofill for him. So we're going to think about what it is that we have to come up with to do this, what information is required. In order to come up with the grams of potassium carbonate, the first thing you're going to need is the molar mass of potassium carbonate. We have done this kind of thing, but this is where we will apply it. And if you pay attention to your periodic table and your good friend the periodic table, it's going to be 2 times potassium, 39.1, plus carbon is 12.011, and 3 oxygens, 3 times 16. Put it in your calculator. Hopefully we can do this all the same and get the same answers. I got 138.2 grams per mole. Again, this question is a little more complicated. It requires an extra step to have to come up with that molar mass. But it's not something that's so complex, but if you make an error there, everything else is in jeopardy. Okay, so what we're going to do is we're going to have to figure out how many grams of the potassium carbonate, but you don't know how many grams unless you want to know how many moles of potassium carbonate are needed. The balanced equation will help us, but we'll need to determine the number of moles of the acid using the volume and the concentration. So let's start with the part that is not a conversion factor. That would be the volume. So 350 milliliters of HBr, hydrobromic acid, times the molarity. We're going to multiply so that the volume is on the bottom. We want volume to cancel out. But again, I'm going to show you how we can not convert to milliliters here without getting ourselves in trouble. So it's 0.5 moles, oh, I should write moles, sorry, moles of HBr per liter. And don't panic, I can't cancel the liters and the milliliters yet, but it's kind of going the right direction. We'll see where that gets us. And, well, okay. Then we need to use a ratio to tell us how much potassium carbonate is going to react with this. Well, actually, now that I said that, we are going to put it in milliliters, convert to liters to milliliters, because otherwise we aren't going to get the right part, because we're going to do grams this time. That's the reason this one needs it. Okay, so 1,000 milliliters in a liter. Pay attention to what cancels. A liter will cancel, the milliliters cancel, and then we should get an answer that is going to be moles of HBr. And plug it all in, see if you get a number. I get 0.175. Why, this tool is funny. Moles of hydrobromic acid. I didn't mean to leave that space there, I just did. Now, that's how many moles of HBr. But given that, how much potassium carbonate is going to go with it? We could have done this all on one line, but I stopped partway to kind of let us see where we're going. So now we need to do a ratio of the HBr to the potassium carbonate, but this is going to be a mole ratio. So moles and moles. So moles of HBr goes on the bottom, so we'll make sure it cancels. And from the balanced equation, apparently we need a 2 with it, reacting with the potassium carbonate. Whoops, moles of potassium carbonate. That's the letters I want in there. Moles. Oh, the tool doesn't talk to me when it's supposed to. Sorry, guys, I'll fix it. Okay, and from the balanced equation here, the moles of potassium carbonate is only 1 for each 2 moles of HBr. Again, pay attention to your units. Everything will be smoother. And now we don't want moles, but we need grams of our potassium carbonate because it's a powder, it's a solid. And so we're going to use a solid. And what do we have to do to get rid of moles? We're going to get rid of moles of potassium carbonate. Look for something that allow us to cancel that out and come up with the right thing. Well, guess what? It's molar mass this time. And so the molar mass that was calculated at the outset in this conversation is going to be inserted here. 138.2 grams of potassium carbonate will be 1 mole of potassium carbonate. Again, if things are all correctly set up, the units will cancel. And now it's a calculator exercise, because who wants to do that without one? Not me, not you. And we'll come up with a number that I get is, only if I can make it right, oops, try again, is going to be 12.1 grams. Is that too many sig figs in this equation, in this calculation? Actually, it is, because our first values don't have that many sig figs. This one has 2 sig figs. Well, that's not very many. And 0.5 molar, that's 1 sig fig. Oh, so in this case, how do you report that to, and I like to play arrow games, to 1 sig fig? That's going to be 10 grams. 10, no decimal, grams of potassium carbonate. Okay, that question was a little more complex than some, but just another idea of how you can relate relate between grams and moles and volumes to understand how things are reacting in a particular example. I hope these examples help you. Please ask more questions. Good luck on your homework. We'll see you in class. The next topics will be on a separate recording.